Okay, welcome back, everybody. Um, I have a great pleasure of introducing Professor Gustavo Dalpian. He is a full professor of physics at the University of São Paulo. This is one campus of the University of São Paulo in São Carlos. Professor Dalpian is in the main campus in São Paulo City. It's the main campus there. The University of São Paulo has many campi in the state, but so he is very well known. He has a lot of experience on atomistic simulations of materials in general. I gave him a hard time. I gave him several papers to study regarding glasses because it's not his cup of tea. He has been working with many other types of materials, semiconductors, superconductors, you name it, single crystals. But I'm sure he did his homework very well. So thank you so much, Gustavo, for coming here, and we all look forward to your talk.
Thank you, Helmut. Oh, no, it's okay. Thank you for inviting me to be here. I'm very happy to be here. And as Anoto said, when he first wrote to me, and Helmut as well, and I thought, and he said, okay, Gustavo, let's talk about ab initio simulation of glasses. And I said, oh, that must be so cool, right? Okay, I'm in, I said. But what I didn't tell them is that I never worked with glasses before. So I'm in the first part, ab initio simulations, I understand quite a lot. But I've been studying about glasses, and you know, Zanotto and Helmut and Hino, at the end I think, if I had money, I would put some of my postdocs working in this because it's so exciting, and I find that there are so many opportunities for doing ab initio calculations of glasses, and I think this is an area to go, okay? So I come from São Paulo, as Zanotto said, and we have a research group there, and our main focus is actually in a little bit different areas. There is one that is, as I'm not from this community, I would like to talk just a little bit about what we do very often here. It's one area is materials informatics that is very similar to what Daniel taught to us this morning, and actually Daniel and I, we are in the same project. We have an INCT, INCT. It's a big project here in Brazil on materials informatics. We are together, and Professor Fazio here is the coordinator of this INCT. So we are together on this kind of things. So we are really into data science and machine learning and things like that. So a lot of people working on this. So another area of research is related to quantum materials, that we have a school on quantum materials next July in São Paulo. And these enter superconductors, for instance, right? And we are also looking for materials for energy applications. So this enters this kind of halide perovskites. And you know, I think these halide perovskites, they are some more or less new materials, and people have been studying it for, it's old, but they were rediscovered some time ago for applications in solar cells. And this kind of material, maybe it's something more closer to glasses that we would say. So one experimental collaborator of us from a Northwestern University, once he came to us and said, you know, Gustavo, these materials are so strange. You know, they look like liquids. And we thought, okay, let's go and try to study it, and their dynamics is quite interesting, and we've been working on that for a long time now. Okay, but so what I'm going to talk to you today, I would like to explain what I'm going to try to make here, what is the objective of this talk, okay? So definitely it's not possible to give you a talk where you are going to understand everything about ab initio calculations. This is impossible. You need a whole course at least, or and a few years of experience in order to get into that, okay? So, but what I would like you to be able to do is the following. First, get some idea. In developing quantum mechanics, they were there. And if you haven't seen, it's a good opportunity. It's easy to find, okay? So, what is the objective of these ab initio methods? What would you like to do in these ab initio methods? We would like to solve Schrödinger equation for a system of many atoms or many nuclei and many electrons. So this is our final objective, let's say, okay? And we want to solve an equation like this. This is the Schrödinger equation, time-dependent Schrödinger equation. Here, for the students here from São Carlos, I think Helmut was the teacher of this, right, for graduate students. And the problem is that this equation is only solvable for the hydrogen atom, okay? So we cannot use this equation directly. But the main idea is the following. If we were able to solve this equation for a glass, we would be able to obtain all its properties and predict all its properties, okay? So this is what quantum mechanics say. This is where we would like to go. But the problem is that we cannot do that. So as I said, it's only for the hydrogen atom. So we need another theory. We need another method. And actually, we have one method that is what we call our preferred method, or the workhorse of electronic calculations, electronic structure calculations. That is a theory called density functional theory, or DFT, that probably you heard about it. So DFT was proposed first in 1964 by Hohenberg and Kohn, and afterwards by Kohn and Sham in 1965, okay? And actually, Walter Kohn, he won the Nobel Prize for developing this theory. It was the Nobel Prize in Chemistry from 1998, okay? So one interesting thing is so the idea of density functional theory, instead of using wave functions, as we were saying here in the Schrödinger equation, we want to use the charge density as the basic entity here in this. So we do not pay a lot of attention for the wave function of the electrons, although we also have this wave function, okay? So taking the density as the basic entity is not something, it wasn't something very new, even at the time of Kohn and Hohenberg and Kohn in 1964. Actually, Thomas and Fermi in 1926 or 30, something like that, if you take the old books, old quantum mechanics books, you are going to see that they already proposed to deal with densities before that. So it's not that it was started only here. The idea of using the charge density was proposed before, okay? And here we have then, this is similar to a Schrödinger equation, and you have your wave functions. You have a lot of very complex terms. You take into account electron-electron interaction. You take into account the interaction between the electron and the nuclei. You take into account everything, and that's the idea. And I don't think I need to go into much more detail here about each of these terms, because it was going to be too hard for this kind of course, okay? And so, but one thing that I would like to say is the following, and this is very important, okay? This is very important. DFT is an exact theory. So if we think that the Schrödinger equation is exact, DFT as well is an exact theory, okay? Formally exact, okay? But the problem is that in its exact form, we cannot use it. It's too complex for us, just as the Schrödinger equation. And then we must do some approximations, and this is where things start to get interesting, okay? We need to do some approximations in this theory in order to make it useful and in order to make it work. And, you know, I like to talk about the approximations because of the following. This is where the limitations of our method are, okay? So you need to understand what are the approximations that are used in order to know what you can get from the calculation. I mean, I'm going to talk about some codes, that very fancy codes, millions of lines, very complex codes to run these ab initio calculations. And if you enter a number there and click enter, after a few minutes, you get an output. And that's a result, you know. But you must try to learn if that result makes sense or not. If what you are trying to infer or what you are trying to learn is within the reach of this methodology or not. You cannot go beyond the approximations that are put here, okay? So the first approximation is Born-Oppenheimer approximation. So just for me to see whether you are in pace with me. So how many heard about Born-Oppenheimer approximation? Okay, very good. Okay, very good. So this Oppenheimer, by the way, is the same Oppenheimer from the movie, okay? So I don't know, so who saw the movie here? Okay, that's better than Born-Oppenheimer approximation. So, but the idea is the following. The movie, young Oppenheimer went to Europe, study molecules, and then he said, oh, they talk about his works, Oppenheimer's works on molecules with Born. So it's this approximation. This is very fundamental from condensed matter theory, okay? This is very fundamental. So the idea is that the nuclei are much heavier than the electrons. And then you can decouple the movement from the nuclei from the movement of the electrons, okay? So we can treat the system as if the nuclei were stopped or fixed and the electrons were moving around these nuclei. It's a little bit deeper than this, but basically from a general perspective, that's what happens. And you know what? This is a very good approximation. Even chemists, they like it. Okay? Even chemists like this approximation. So this is very good. Usually we do not have problems with these approximations. So I wrote to Danielle this weekend, and my question was the following. Danielle, do you have hydrogen inside glasses? And he said, oh, sometimes when it's wet, you can get, during the rainy season, you get hydrogen inside the glasses. Okay, and then, you know, sometimes if you want to simulate hydrogen inside some systems, then you have to take care with Born-Oppenheimer approximation, okay, hydrogen. But otherwise, for all other elements that you would like to look for, there is no problem. So Born-Oppenheimer, usually you don't have to worry about it, okay? The second approximation that I like to say, oh, by the way, I like to say there are three approximations only when you have to deal with DFT, only three. This is a lie, obviously, right? But only three that I consider more robust and important. The other are technicalities. There are dozens of other approximations. But there are three that are very important that you must learn and you must think in order for you to think about ab initio calculations, okay? The second one is pseudopotentials. It's expensive to treat all electrons of a system explicitly, okay? So we just substitute the core electrons by some smooth potential. So it's something like this. Suppose you have silicon, electron configuration of silicon is this, 1s2, 2s2, 2p6, 3s2, and 2p2, 3p2. So we treat this as a core, and we only look explicitly for these extra 4 electrons, okay? So that's the idea of, and so we substitute here, if you look for the wave function, this is wave function, the red one is the wave function, the blue one actually is the wave function as a function of radius. So we substitute this region here by a smooth potential, pseudo-potential, pseudo-wave function, and then it works better, okay? So this is also good approximation. Usually you don't get many problems with this. And the main problem of DFT is in this third approximation that is related to interaction among electrons. Electrons interact among each other, so you have exchange interaction, you have correlation, you have some very complex stuff happening. And DFT is not very good in treating this kind of interactions. So we must put we must use some kind of approximation to treat these systems. And this is the exchange and correlation potential, or the exchange and correlation functional. So what we do is the following. We fit this potential. So this is not fully ab initio, I have to say. Okay, so this is where ab initio maybe, so this is the weak part of DFT is treating with this kind of systems, okay? And we have a lot of flavors for this kind of approximation, okay? So we have, let's say, local density approximation that's called LDA. You are going to read in the papers, oh, we used LDA, we used GGA, we used whatever. And so this was proposed in 1980, more or less, and it's okay, so people do not use this anymore. And then there is one that is called generalized gradient approximation that was proposed in 1990, more or less, 86, maybe 90. And then this is, usually most papers you're going to read use this kind of methodology. And then there are hybrid functionals. Chemists love these hybrid functionals because you can put some more parameters there and then they like it. And the newest thing are these meta GGAs, or that is one method, is scan method. So if my new students, when they start a new project, everyone is starting with this kind of approximation nowadays. So if you read a paper, this is, if you would like to start some new calculations using DFT, you should start from here. Okay, that's the state of the art nowadays. It's a little bit more expensive computationally, but that's where people are working now. Okay, so this is very basics of DFT, but what I like to say is DFT is considered nowadays a very mature methodology, is very reliable. Okay, there was this paper published in Science already in 2016, so it's already 8 years, where they took several different codes and they simulate the same material, that is silicon here, and they all get the same result. That's perfect, because before, each one would get a different result. So they say, oh, you see, we are getting different codes, different groups, we get the same results here for the lattice parameter of silicon. So we get the same results, so we are converged, or everyone is at the same pace, we are doing the same theory, and so we get a good method to try to simulate this. And there are a lot of cases of success, and I like to put this one is a science paper from 1989 from Marvin Cohen from Berkeley, and he would like to try to find a material that is harder than diamond. This is fancy, isn't it? So he made his calculations, and he got these materials, beta, C3, and 4, and afterwards they learned that when nanostructured and whatever, it would be harder than diamond. But so the idea is just to show that this is a very mature methodology. Okay, so what happens is you have a very mature methodology, and here I would like to make a parenthesis, okay? The point is the following. I would like to focus this talk on glasses, and that's what, what you asked me for. But the point is that all methodology for doing ab initio calculations was made for crystals, okay? All methodology, so when you see a paper doing ab initio calculations for glasses, they use the tools that people use for crystals, and they try to apply it for glasses, okay? So there are things that wouldn't be needed in glasses, but you see in the methodology of the paper because we are using a method that was developed for crystals and try to apply them for glasses, okay? And that's why I have to tell you, and I'm going to tell you a little bit about crystals, how we do ab initio calculations of crystals, and then afterwards, you are going to be able to understand why do we do that way, why some methods have to use this or that, and why we have to do some approximations, and why people are talking about some parameters that in principle were not needed at some point. As to use computer methods or computer simulations, to develop materials in a much faster way, okay? And to discover materials in a much cheaper and much faster way. And this changed the way we look for materials from a computational point of view, okay? So what happened is the following. The first thing that happened, Daniel talked about this morning during lunch, we talked about this, where a lot of repositories for materials were launched, okay? So this is a paper from 2019 talking about materials repositories after the materials projects. And you see, none of them are in the South Hemisphere. We just published a paper where we have the same catalog of ab initio calculations, but you have some important stuff here, and I cannot read from near nor from far. So I'm in a position here. But probably the main important database, for those who are older, I put his by myself. Actually, there is a database of materials, Landolt-Bornstein. It's from 1882. I don't know if you have already seen. Hino probably saw the Landolt-Bornstein, some very thick books. Probably you guys as well. They were databases of bulk materials, okay? And the main repository of materials is this guy here. It's the Materials Project. And this is something fascinating. And I have a small video here to show you and this is an open database where you can get ab initio simulation for materials. So you see here, this is the number of materials they have. They have 150,000 materials, okay? This is a number of materials over time. They calculate different properties. This is quite fast, sorry. Then you can start exploring materials, and it opens this periodic table when you can select. I've chosen silicon oxide. That was a kind of glass that I thought would be interesting. Let me pause here, it's so fast. And then you get more than 340 entries for silicon oxide. Most of them are crystalline, all of them are crystalline. And it's interesting that some of them are not stable, not even synthesizable. Because why is that? Computer accepts everything, okay, guys? If you're going to do computer simulations, computer accepts everything. You put the atoms there, and you click enter, and you get a result. And that's what they do here. So I have chosen one of these silicon oxide just to show you what happens. You have symmetry. In glasses, you don't talk about symmetry. But just to show you what we are talking about when we look for these databases. So I have chosen this silicon here, silicon oxide. And if we click on it, we get the crystal structure here. Okay, so you see that it's crystalline, and you get properties such as band gaps. You have all the lattice parameters. So all this is free. You can enter there now, and you can download all these properties for free, okay? All structural properties. Also, predicted stable. So this one, they say it's not stable, so it's calculated, but it's not stable. It shouldn't be synthesizable. This is band structure for calculating band gap of the material. Okay, you have magnetic properties, charge density. You have several diffraction patterns. So everything generated on the fly for 150,000 materials, okay? So you can look for mechanical properties. Maybe this is important for glasses. We can calculate stiffness tensors and other bulk modulus. We can calculate all sorts of things from these ab initio calculations. We can go to other materials such as aluminum oxide, okay? But basically it's the same thing as before, okay? So I'm going to jump this. So how these repositories are populated? So you see that there are more crystals here, there are more simulations here than materials that exist in nature. Okay? If you take the glass repository, each entry is a glass that was realized, I understand. Here not. We can simulate materials that do not exist yet, okay? So take an example here. Let's take this material. It's one of my PhD students is studying this, is calcium aluminum fluoride. It's a very wide bandgap material. And then, so this has been synthesized and has been studied. Okay, we know its properties and crystal structures. Then we take and we substitute calcium by other chemical elements similar to this one. We substitute aluminum by other elements that are similar, and we substitute fluorine by other halides. And we simulate all all possible compositions, and we get the properties of these hypothetical materials. Not all of them are going to be synthesizable, but we can predict if they are going to be synthesizable or not, okay? And then if you look for these databases, so suppose this rectangle illustrates the number of materials in the database, okay? There is a huge number of materials, but only a small fraction of them are known or have been synthesized. Another fraction just, they don't matter, and some of them are predicted to be thermodynamically stable, and it would be worth trying to synthesize them, okay? So now we have in the database a lot of materials that we predict are stable, we predict they have interesting properties, but they have not been synthesized yet, okay? And we see this as a huge opportunity for developing science. And the idea of the materials project, or the Materials Genome Initiative, was to think about a way to accelerate the design and the discovery of new materials. And so the idea, as Danielle said this morning, was to skip this Edisonian. Edisonian comes from Thomas Edison, and it's of the idea of trial and error. So we do not like to try and see if it works, okay? We would like to suggest only materials that are really feasible and could be synthesized at some point. So we understand that this kind of methodology can increase a lot the speed of development of new materials. So this is inverse design. This is what we call inverse design. So in standard approach, you go to the lab and you synthesize your material and you get some new material, and then you measure its properties, and then you think, okay, where can I use this material? Okay, so this is the standard methodology. In the inverse design methodology, you ask yourself, what is the property that you want? And then you go to a database, the supermarket of materials, and then you see which materials fit the property that you want, and then you try to synthesize the material that you want. So we are doing this during pandemics, so people came, one example, people were interested in LEDs that would emit in the UV region. So we have red LEDs, LEDs, you have blue LEDs, you have green LEDs, but we do not have many LEDs that emit in UV light, right? So people were trying to do this. So what do you need in order to get this? You need a large band gap, you need some effective mass in some specific characteristics, and that's what people did. So you go to the supermarket, you try to find a material that has wide band gap and the other properties as you want, and then you try to simulate this kind of materials, okay? Or you try to build this kind of materials. Oh, let me drink a little bit of water here. Okay. So this is where we stand right now in this area of ab initio calculation of materials. Just to get into some specifics here, some ideas of what we do. I would like to talk a little bit about the codes that we use. Okay. So this was taken from this paper. It's a very nice review from DFT and machine learning. Actually, if you want a very good reference for this kind of methodology, go to this paper. It's from some Brazilian colleagues, and it's actually got a lot of citations already, and it's from 2019. So if you ever want to run some ab initio calculations, you should get a code that do this kind of trick, and these are probably the most interesting codes that I could offer you. So we basically use this one called VASP, okay? It's after Vienna Ab Initio Simulation Package. So this is commercial, you have to buy it. For universities, it's around, I think, 6,000 euros, something like that, the price of this package. And this is probably the most complete package for ab initio calculations. So they have computer scientists working on this, so it's very efficient. You can run large systems very fast. It's parallelized, and so it's a very good tool. This is the one we are using. If you do not want to buy it, you can use Quantum Espresso. That is an open code, and it does the same trick at the end. Maybe it's not as efficient as VASP, okay? And it doesn't do all options as VASP does now, but it's also a very, very good code, okay, for ab initio calculations. VASP is probably a little bit better if you want to do ab initio molecular dynamics, then you should go to VASP. Actually, if you want to go to ab initio molecular dynamics, you should use this code called CP2K. That is ab initio, and it's basically written to run molecular dynamics. These materials, these other codes, they were written to study crystals, periodic crystals. But this CP2K was built to do ab initio molecular dynamics, okay? And okay, so suppose you get one of these codes, and now let me switch from crystals and go to glasses, okay? So what we do, we want to run a system. We want to perform some ab initio calculations of glasses. So the main challenge, without any doubt, for running ab initio calculations of glasses is that you need an initial crystal structure for your system, okay? So you need, basically what you need the type of atoms that are in your glass or in your structure. You need the position of each atom, and you also need the lattice vectors. So, and then you say, okay, Gustavo, why do I need lattice vectors? This is for crystals. I mean, you talk about a unit cell. Like when you study solid state physics, you remember first class, simple cubic, FCC, hexagonal, several different lattices, right? And then we need to tell our code what is the lattice we are working with. And then we say, okay, Gustavo, why do you need that? And that's what I said before. It's because we are borrowing a method that was built for crystals to study glasses. And it's all code. All codes are like this, okay? So we need to do this kind of thing. Well, we have some solutions to do that. The first thing, we need to build a box that we say, or a supercell, okay? And the idea is that if you want to simulate a glass, you should start from some very large cells, okay? So suppose this is a perovskite that we are studying. This is a simple cubic lattice. So this is a crystal, as I'm just using to explain it to you. Why do we need this? So this is A lattice parameter, B lattice parameter, C, and you have the position of each atom, okay? So if you want to run a glass or something more complex than a just simple crystal structure, you need to do a supercell. So you do not use this minimal structure. So this minimal structure only has 5 atoms on the unit cell, okay? So it's this one in the middle, this one, and this one. Only 5 atoms, okay? But we do a supercell, and then we use this supercell to simulate our material, okay? So supercells are very useful. Suppose here, just for you to, suppose you want to run a system that has only one type of atom, okay? And then you can use, look at this left side, only one type of atom, that is atom type red here. So you have one atom per unit cell. Okay, you can do several larger cells as well, and it's going to be possible to simulate the material as well. The idea is the following. If you want to simulate an infinite crystal, you do not have to simulate all 10 to the 23 atoms on it. The idea is that you have a minimal cell, and if you get the property of this guy here, all the others will be the same. So you can only replicate them over the crystal. Okay? Now suppose you have two types of atoms, and you want to make a glass that is silicon oxide plus 1% of sodium, or plus 25% of sodium, let's say. And then you use this glass, this supercell, and you put a white atom here that is sodium. So now you have 25% of sodium, and you can simulate this. If you can do more, even more. So here you do a 3x3 supercell, and then you have one white atom, and you have 8 red atoms. And using this, you can change your stoichiometry of your systems. And you can even run surfaces, you can run isolated molecules. And if you have a large enough supercell, you can study glasses, okay? So the point here, in order for you to be, oops. Okay, we are back. So the point here is the following. If you want to simulate a glass, you do a large supercell, you throw your atoms inside, and you try to get some structure. This is some structure that was taken from a paper that I'm going to show you in a while. And then you simulate this material, you solve the ab initio equations for this material, and in principle you get all the properties from this material that you would like to get, okay? Okay, so this is the challenge, the first part of the challenge, or the first part of the solution of the challenge. And the second part is, this is for getting the lattice vectors. And the second challenge is getting the position of the atoms, okay? So the solution for getting this position of the atoms is connected to what Hino told us this morning, that is molecular dynamics, okay? So Hino taught us about classical molecular dynamics that use Newton classical mechanics to solve the equations. Here, we can couple ab initio calculations with molecular dynamics. So we get ab initio molecular dynamics, and you solve your equations. You insert Newton's laws, but you also solve Schrödinger equations, okay? And it's interesting because if you look, and Hino probably knows this, there are so many recipes for getting this, the position of these atoms, so many different ways for you to infer about the crystal structure, or so this is a question, my understanding is a question of taste. It doesn't have one that is correct and one that is incorrect. And and he proposed a way to get from quantum mechanics to calculate forces on atoms. And so this is a paper published in Physical Review, and I still give this paper to my students, you know, for them to read. And it's a very nice paper because, you know, it doesn't have any reference. It's a paper published without any reference because it was quantum mechanics, 1939. It was more or less well established. So he would cite Schrödinger. He could have cited Schrödinger, Heisenberg, something like that. But he decided to write a paper for calculating forces on molecules. The title is Forces in Molecules. And there is no reference. So it's a paper that is very easy to read, you know, because it's just basic quantum mechanics. If you have some basics in quantum mechanics, you'll be able to read this paper relatively easy, okay? And so this is how we calculate our forces. Actually, people say, just to be fair, published his paper just by himself. Feynman published his paper just by himself, but Hellman developed some parallel work at the same time, actually 1 year before. But by that time, papers wouldn't go. If you publish today, maybe people were going to read it only in 1 or 2 years because they didn't have internet, right? So I think Hellman's paper was 1 or 2 years before Feynman's paper. But nowadays, if you read books, you are going to hear about Hellman-Feynman forces on molecules. Okay? Well, so this is what we do. What we do not, what people who run ab initio calculations for glasses do. Okay? And then I went to the literature to try to find some representative papers that use this kind of methodology to simulate glasses, okay? And you know, I think this was one of the most interesting papers that I found reading this literature, okay? So it's a paper from two scientists, Lee and Botu, and they are from Corning Technology. That we are going to have a talk from Corning just after mine. And this is a paper from 2022, so you see that this is a very recent paper. And you know, it's Computational Material Science. The name of the journal is not any fancy journal. It's people. I like this journal, but it's already old. It must be 30, 40 years already. It doesn't have a very high impact parameter, but it's a very solid journal, let's say, very traditional journal in the field. And this paper is not highly cited, but reading it, I think this was one of the papers I liked most because it was clear, and we see that they are working in the state of the art. Okay, they are doing some very serious work here. So the idea is a high-throughput ab initio study of several different glasses, and they try to calculate refractive index of these glasses from ab initio methods, okay? And this is what I like a lot. So why I like this paper? Because when I read the methodology, I found it very useful. And so let me stop here a little bit, because when my PhD advisor said, when I was doing my PhD, and probably you guys already heard this, something similar, and people say, you should not make a presentation with a lot of text in a slide. This is not good for your presentation. Then you look here, there is a lot of text, okay? But there is a purpose here, guys, okay? So the idea is the following. I copied here the methodology section of this paper, okay? That I think is a very representative paper of what you can do if you want to do ab initio calculations of glasses. This is a good paper to start with because it's very clear and very straight, okay? So I copied the methodology here just to show you here. I'm going to highlight some of the parts of the methodology, and I'm going to try to tell you guys to translate to you guys what it means, okay? How they dealt with this. So whenever you run a paper like you read a paper like this, in principle, you are going to be able to understand better, a little bit better, I hope, what they have done, okay? And as it's going to be recorded, I think it's useful as well. So the first thing, they choose some chemical elements to get a specific stoichiometry, and they are randomly placed in a constant volume box. So this is the first step that I just told you about. If you want to run some ab initio calculations, you set your composition and stoichiometry, and you throw your atoms inside, okay? Then, look, each structure starts with a constant temperature simulation of 4,000 Kelvin. Okay, stop, let's stop. So this is very high, isn't it, 4,000? Right, so can you get this for doing glasses? Probably not, right? So this is huge. So this is an important thing, guys. When you do ab initio calculations, the absolute temperature, it doesn't necessarily meet what you have in the experiment, okay? So sometimes you have to go beyond. When you look for phase transitions, so we can try to calculate what's the temperature where a crystal will change from FCC to BCC, something like that, suppose you have a phase transition. Ab initio calculation is very hard for them, for this kind of methodology, to get the precise temperature, the precise transition temperature. Why is that? Because of the approximations I told you in the beginning, okay? So I told you about 3 big approximations, and the last one was the exchange correlation potential, the way you treat the interaction among electrons. So this is very tricky, and sometimes because of this kind of approximation, you will not get a very good number for these temperatures. So that's why they start with a very high temperature, 4,000 Kelvin. They leave it there for some time, okay? Afterwards, they start quenching. They start decreasing the temperature. So you have something that is random there, atoms randomly distributed. So you start decreasing the temperature until you get a structure that you can simulate. So, and they want to cool down to 300 Kelvin, from 4,000 Kelvin to 300 Kelvin. And here comes one thing that Hino said, and Zanotto also said, that is the different time scales of simulations and experiments. So look here. So the cooling rate was 200 Kelvin per picosecond. So, okay, so it's hugely fast, okay? But so this shows that the times, we are talking about different time scales in simulations and in experiment. And this is a big challenge that, as Zanotto said this morning, even huge computers, supercomputers that we have today, they cannot deal with this very well, okay? And at the end, they say that they do this procedure for many different glass structures. You take a stoichiometry, and they generate 5 different structures to get good statistics, okay? So that's what people do, okay? So this is, now, so you see, now if you take a paper, look how good was this talk. If you take a paper and you read the methodology section of an ab initio paper, you're going to understand a little bit what it's talking about. Actually, it's not like this. Sorry for this, guys, but I took another one, just that it's even more complex than the one before. Sorry to put such a burden on you, but to watch these slides full of letters. But this is the methodology section from another paper. And this is where I'm going to go very fast here, but there are some technicalities that can be way more complex than what we talked before. So here, actually, we can understand, we can correlate all these things with experiments somehow, okay? But there are things that we cannot correlate with experiment. For instance, take this paper. I'm going to show you this paper afterwards as well. So this is, they use the VASP code, as I told you, okay? So this is easy. They use GGA, as I told you, so this is exchange correlation now. Functional, so you know what are the limitations from your code here from this. They use spin polarization. If you put magnetic atoms, you see that I only mentioned silicon, oxygen, sodium, aluminum. However, if you put transition metals onto your simulation, you need to take special care. You do not run the simulation as for silicon oxide. You have to turn on some flags in the code that is spin polarization, okay? So here they use the PAW method, what was that approximation for pseudopotentials. Plane waves, is like, this is some other technicality related to how reliable your calculation is. K-point, oh, this is pretty interesting. This is very interesting. When you work with solids, with crystals, we usually look for the properties in reciprocal space. Okay? And all these codes that I told you, they all work, they all do the calculations in reciprocal space. Then you said, okay, but glasses, we don't care about the reciprocal space. So there is no periodicity. When you have a crystal, you Fourier transform it and you go to reciprocal space, okay, momentum space. And here, it's for glasses, it wouldn't be needed. So why do they talk about reciprocal space in a paper about glasses? It's because, as I told you, the codes were written in such a, well, they are using codes that were written to run crystals. And then you have to think about it. You have to know about it. It's not, if you want to use these codes, it's not because you are using glass, you do not have to pay attention to these permits. You have to pay attention to them, okay? Hubbard correction, this is getting very complicated. So when you treat transition metals, you have d electrons, and this DFT, GGA, in these methodologies, they are not very good dealing with transition metals, okay? If you take rare earths, F electrons, it's even worse, okay? So we struggle, we can do that. We can do that, but you cannot use just the standard recipe that comes with the code and run it. You have to put some extra spice in the code, extra ingredients in order to get your, that's Hubbard correction, okay? What else? Hybrid exchange correlation, they made some tests and so on, okay? Okay, enough of sections of methodology. Let me talk to you about the second challenge of our simulations. That is, they are really, really expensive. Expensive from a computational point of view, okay? So this is probably the biggest problem of DFT calculations. They are very expensive. When I collaborate with my experimental colleagues, you know, they do the experiments very fast, and then they say, okay, Gustavo, now it's your time to run the calculation. And then it takes 3 months for me to get back to them, so they are already bored. But that's how things works, okay? So we only can run very small time frames of the order of 100 picoseconds in this kind of simulations. We can run a few hundred atoms, 300, 400, 500 atoms, using the largest supercomputers we have available. So we use this Santos Dumont supercomputer in Petropolis. It has, we usually use hundreds of CPUs for weeks to run this kind of calculations. So they are very, 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 very expensive, okay? And this limits the applications that we have, okay? Well, I was going to talk to you a little bit about some example, but these are not glasses. These are calculations that we run for perovskites, okay? But basically, we have we made very long simulations, but I'm going to skip this because let me go to another part here so where can we use this kind of simulations? Well, I've chosen a few papers to show you about examples of this kind of simulations. I think there is a lot of opportunities for looking for electronic properties of glasses, okay? So looking for color centers, things like that, it would be a good opportunity. Charge trapping in glasses, we also could learn, okay? But at the end, I'm going to talk to you more about these machine-learned interatomic potentials. So let me show you some here. So this is, again, the paper from these guys from Corning that I've told. They wanted to calculate the refractive index of several glasses, okay? So this, I bet this was a huge work because see this table. They have made a lot of different samples, a huge number of samples. And this is actually important, so please pay attention. So this is interesting. So this is a company. We heard this is a very big company. I bet you all guys learned about this. And they published this paper two years ago, okay? And they made ab initio simulations for a lot of different stoichiometries of glasses. I cannot read. This is pure silicon oxide. This is 80% of silicon oxide and 20% of sodium oxide. A different stoichiometry, 0. I cannot read here. Can you read? Sodium, titanium, and silicon. There are some that are more complex. Fluorine, potassium, titanium, and silicon. And niobium. So they run a lot of ab initio calculations for a lot of glasses and calculated the refractive index for all of them. Here are just some examples. This is just a very simple glass, 20% of sodium and 80% of silicon. And then at the end, you are going to get some result like this, where you have the refractive index as a function of wavelength, okay? Here you have a snapshot of the crystal structure and so on. So what calls my attention about this paper is the following, why I liked it. It's very robust, the methodology is very good, but they did a lot of calculations, but you know, I looked for other papers from them, I couldn't find something. But you know when you are ready to do something much bigger with the results you have, and they have not published. Probably the company has all this cool information that you could get from this, but it's just not published. You know, they hold them for themselves. But this is a typical paper where you look what they have done, you see that it's a great deal, you see that's important, robust, and you see that it would be very easy to go one step beyond and get a lot of properties and predict a lot of things. And they have not gone that way. Actually, they have not published that way. But probably it's somewhere around, right? It's somewhere around. Well, so why I say they could go beyond that? It's because this is where I would like to put the state of the art in glass, ab initio glass simulation nowadays, okay? So the idea is the following. It's to put together machine learning with ab initio calculations, okay? So the idea is that you first run the ab initio molecular dynamics for the glasses that you want to study, okay? You run all this, you make a dictionary of ab initio calculations, a repository of ab initio calculations, and then you use this information to train machine learning models to reproduce these ab initio calculations, okay? So these trained models, they are as efficient as the ab initio calculations for doing the molecular dynamics, and they cost only a fraction, or it takes, computationally cost only a fraction of what the ab initio calculations. So you can run larger systems, and you can run longer systems with these molecular dynamic trained potentials, and with ab initio accuracy. So this is the point. So that's where I would put the state of the art of this kind of methodology nowadays. And this, you know, look, these guys, they have made ab initio calculations. They have a lot of data. They have a lot of data. They have made ab initio calculations for several different classes, different compositions, different type of atoms. So it's only to take this data that they already have and train with these machine learning algorithms in order for you to be able to do all this again in a fraction of the time you used before. You can run much larger systems, okay? And I bet they have trained also other type of atoms, if not all atoms, okay? Because that's what big companies are doing today. They just train everything. So I think there are huge, huge opportunities here for doing this kind of things, okay? So just for you to have an idea, if we go to papers, like Hino cited in his talk, several different potentials from classical fields, Leonard Jones, Vashista, and many others. So these are very traditional potentials that people have been using for some time, right? And people like these potentials. They test one against other. But if we go to machine learning potentials that is similar, okay, we only have information for very simple materials. This is silica, only silicon oxide. So this is open access, so you can download the potential and you can run the same ab initio the same molecular dynamics they run here. As Hino said this morning, it bothers a little bit. Okay, that when you do Leonard Jones potential, you know what each term means. You know what's happening there. Here it's a black box. Okay, it's a potential that was trained in this black box, but at the end it works. Okay, and you get the real results. And so this is probably one of the papers that are being mostly used, and so people are using this kind of methodology. And they made a lot of calculations. They do just as the other paper that I've shown you. They start at, this is even higher, to 6,000 Kelvin, okay? Even higher. So they throw the atoms inside a box at very high temperature. They let the atoms try to fight to each other to find the place where they are happier, okay? And then they cool down and they get some structure. And then they use this to train the machine learning potentials and get the potential. And then they cycle among different structures. And this is also, let me say, this is almost alchemy, you know, because they have some recipes, and then they said, I was reading the paper, actually in the supplementary information, and then they say, then we take some crystalline information from several different phases of silicon oxide, and we put together. We take dimers of silicon, dimers of oxygen, we take clusters. So you have to give enough information for your machine learning model to be able to run this kind of calculation. But I would say this is the most used paper nowadays. So let me jump this. So this, for instance, is a paper, and this is a very good journal. Nicola Marzari is a leader in our area of electronic structure calculations from EPFL, and he used that potential, the one that I just told you, to calculate thermal conductivity of glasses from ab initio information. Okay, so you see this is a paper, to 2023, last year. Okay, so very recent. So this is state of the art, okay? So this is another paper that does machine learning for calculating glasses. They try to get what is where does this sharp diffraction peak they observe here. This structure factor, they look for this first diffraction peak here, and they try to infer where does it come from, and they have some argument here that I do not follow exactly, but it's the periodicity between the ring centers and the shape of the rings. Well, you can infer some physics from this kind of models, okay? And then there are other papers here. This is another one. You see, it's a neural network interatomic potential for silica glass. So you see, it's the same thing as the other one that I mentioned to you. So it's just, as Hino said, there is Leonard Jones, there is Vashista, and so on. So that one was one that is being highly used. This is another one that is being used for glasses as well. And then they do their stuff here, calculating several different properties from these, usually in this case, they are structural properties, okay? Well, as I go to the final part of my talk here, I would like to leave you with a message to think beyond, okay? So the idea is the following. What I've shown here is that we have a good methodology to try to understand the properties of materials, of glasses, from an ab initio perspective, okay, using quantum mechanics, considering electronic degrees of freedom and so on. I have talked to you about the limitations of this kind of methodology. That is very important. You have to take very good care of these limitations. You cannot think, computer is going to tell you whatever it wants, but you have to learn about the limitations in order to interpret if the result you're getting makes sense or not. 4,000 Kelvin, 6,000 Kelvin doesn't make sense, and you need to know why, okay? But it's useful. And when we look for crystals, we want to predict some properties, and what I have shown you is that we can use the information that we have to predict the properties of new materials and to try to optimize the properties of these materials. I think we have seen this this morning from Daniel's talk and from Hino's talk, that these computer simulations, they can be used to predict the properties of things that, of new materials that have not been synthesized yet, or proposed new materials. Daniel has proposed a new material that has not been synthesized yet. Okay, and when we do that, we are talking about, I like to talk about these kind of paradigms of science, okay? So what I have shown you here is that ab initio calculations are using a lot data science to perform the calculations. So the first paradigm of science is empirical science, that is experimental. I told Zanotto that if I were born again, I would like to be an experimentalist, but he said, keep with the calculations, it's better, right? Second paradigm is theoretical science, okay? So that's where you have Maxwell equations, Schrödinger equation that we learned, that we talked about, Newton laws, and so on, okay? Third paradigm is a computational science, that is density functional theory. If you take density functional theory just by itself, ab initio calculations, we sit here in the third paradigm, okay? And now there is this fourth paradigm of science that is the one based in data science, is that where we are starting to use data science tools to study materials, to do ab initio calculations, okay? But nothing says that we cannot go beyond this, fourth paradigm. And this is, I've copied, so this is, it's referenced here as Microsoft, so this is, I do not have the exact reference, but this is a paper published in Nature in January, I think, or February of this year, okay? And I took this slide from this reference. It's available on YouTube. You can find this. And he talks about this idea of predicting new materials with better properties, okay? So what we do now, what we are doing is more or less this. There is some known space that is the databases that we are using. We are using databases for crystals, we are using databases for materials. And we would like to use this information to get materials with better properties. Here they cite high TC superconductors. It's a superconductor at high temperature. But you can think about some property of glasses that you would like to get. So a glass that never breaks, a glass with very small refractive index, and so on. Okay? So the point is that if you look for the methodologies we are using now, these data science methodologies we are using now, they are based on what we already know in the materials that we already know. So we look for the materials we already know, and we try to predict what would be new materials. So this is called, for instance, screening, okay? So when we do screening of these materials, when we learn these molecular dynamics potentials of these materials, we do this to speed up the simulation, and we can learn very good science from this. We can get fantastic materials from this, but we cannot go beyond this point, a certain point where these materials with wonderful properties would be, okay? So we'll still reside within the family of materials that we know. So if we want to go beyond, we have to think about other type of methodologies in order to go to make this paradigm shift. What these guys from this Nature paper from this year, they said that this would be generative AI, artificial intelligence, and this might be something that we should look for and try to, this is future, okay? And try to plug our methodologies with this in order to us to leap into these new families of materials that have not been discovered until now, okay? So just to finish, I think we have huge opportunities for ab initio simulations of glasses. As I said, I told Zanotto, you know, if I had money, I would put one of my postdocs to run ab initio simulations of glasses. I think there are a lot of opportunities to look for electronic properties of glasses. I haven't seen many papers looking for this. And certainly, I'm sure companies have these very general machine learned models already trained, okay, because they have all the information to do that. But I think there is a lot of potential, there are a lot of opportunities to train these new machine learning models. And why not? Keep in mind, if you want to think something for the future, 10 years, maybe you are going to start hearing about generative models based on machine learning. Okay? That's it, Zanotto. Thank you very much.
Thank you very much for this beautiful lecture and also for giving directions for future research. Questions? Yes, please. This is my exercise for
Hello, I'm Vera Kerling from the University of Erlangen. My question is, how good are the predictions? Like, you can predict the properties of a glass composition with this simulation. How good is the prediction also compared to a crystal? And where is the disagreement between the predictions and the actual experimental data? Like, in which systems or with which conditions?
This is actually a very good question. Okay. So depending on the property you are looking for, you can get better agreement with experiment or not. So what we would like to do is to get some type of agreement with experiment. So if you look for structural properties, so as we have shown, the ring density or number of atoms average number of atoms in each ring, and if you take NMR structural properties and you try to compare, if you take some kind of vibrational spectra of the material, usually you are very good when you go to structural properties, okay? With any approximation that we use, either the hybrids or the GGAs, or usually you get very good agreement with experiment. For instance, lattice parameters or bond distances, usually the error is around 0.5%. It's not on top of it, but it's very small. We think it's very small. It's very good comparison, okay? So very good for structural properties. When you go for electronics properties, you have to take a little bit of care, okay? So for instance, the band gap of the material is usually underestimated with this kind of simulations that we do. And then when you look for refractive index, for instance, you have to apply some kind of correction to be able to compare it to experiment. But even with this limitation, you still can learn a lot because, you know, what happens is the absolute value of the band gap is not very good, but the shapes are all good. So usually you get just the peaks a little bit shifted, but you can get all the peaks that you want to get for optical properties, for instance. So in principle, electronic structures are a little bit tricky, but you can still learn a lot from them. And there are new functionals, but then it's more expensive. When I say expensive, it means it takes a lot of computer time, okay? Then it's more expensive to run these calculations. You have better methodologies that I have not even mentioned here that are very precise, but they are certainly beyond the scope of classes right now. Okay.
Just a follow-up question. The paper from Corning that you have mentioned, did they compare the predicted properties with experimental data? Because those are well-known glasses. I mean, some of those glasses are binary silicates or so that I'm sure they're well-known.
Yes, I think they have not.
No?
Yes, so it hasn't called my attention. So what they do here is they try to compare the ab initio results with classical potentials.
Okay.
So, and so this is the comparison that they make, not with experiment directly.
Yeah, because the refractive index is well known. I'm pretty sure that somebody has measured the refractive
definitely,
index
absolutely,
of
absolutely.
those glasses. You know,
But they use the density from experiment. That's what they always use.
the density was from the experiment. Pedro.
Gustavo, you have the machine learning approach. You need to train your system. You train it using DFT calculations, things like that. After that, you have a machine learning potential, and you said that with this potential, you can simulate it larger and longer time. But can you get extra results without having found using DFT? For instance, do you understand my question?
Yes.
Or is just the same, or just the same results, just larger system and longer system?
Yeah.
Is there any new?
Yeah, this is very good. This is another very good point, Hino. So the question, and this is a limitation for machine learning. You start from ab initio calculations, and I mean, you can, in principle, you can only simulate from what you have learned, okay? So from what you have simulated from ab initio results. But let me show you one example. So I'm going to give you an example about that we are studying for two-dimensional materials, if you allow me, Zanotto, to give an example that is not from glasses. So we trained a machine learning potential. We did molecular dynamics of two-dimensional systems. Let's say graphene. Graphene is fancy. And then we want to look for oscillation, for vibrational modes in graphene, in a two-dimensional material. And you know, these oscillational modes, they are very well known. I mean, there are oscillations, the G mode, and so Raman usually gets this very easily, okay? So this is, we can get from ab initio calculations very easily. However, there are some very slow modes on 2D materials that are related to long wavelength ripples. So you imagine there are some very long wavelength waves on the material that distort this material. There are some beautiful pictures that they show graphene oscillating, right? And so these very slow modes on graphene, these very slow oscillations, we cannot get from ab initio molecular dynamics because we do not have time enough to allow for this simulation, and we cannot run them large enough. But if we make a large supercell and we let it run for a very long time, all the physics is there. And then we can see these very slow oscillation modes that we wouldn't get in the in the original ab initio calculation. Same thing for glasses, I understand. If you have some dynamics that is very slow, and you wouldn't get it in the standard picoseconds that we run, in principle, it should be there. You should get these modes from these trained potentials because you can leave the calculation running. Not the crystallization time yet. I think we cannot get to second, definitely. It's not even millisecond. This still takes a very long time. But I think we can go beyond and we can get new science from these potentials, yes.
Very good. Come on.
Yeah, thank you very much, Gustavo, for this really, truly inspiring and visionary lecture. My question appears to be rather simple, and you probably have a good answer for this. You let the simulation run for some time. When do you know, actually, what is the criterion to say, well, this is long enough, and now the system doesn't change anymore? So,
when do we know it's long enough? Okay, yeah. This is a very good time, a very good question, Helmut. Usually, I have something here that I haven't shown you. Well, when we run molecular dynamics, usually you have two different steps. The first is a thermalization step that you want your atoms not to remember where they come from, so to get the random enough. So, and then we only use the rest of the simulation, okay? So I don't, as far as I know, there is no exact answer to this question, Helmut. It's basically a matter of taste from the person who is running the simulation. So here, for instance, we run very long simulations. This is very long, okay? It's 100 picoseconds here. Oh, it's not showing. Oh. Okay, so let me see again. Oh, now yes. So these are several simulations. So these are ab initio simulations of the perovskites for different temperatures. So let me see. This is 150 Kelvin, and then start going up until 500 Kelvin. And we run it for 100 picoseconds. So usually here, we take the first 40 picoseconds and we discard those structures, and we only take the last 40 picoseconds. However, if you look, if you look here, let me go back. If you look here, this is what we did. If you look here, this time is only 5 picoseconds. So it's much smaller than what we are using in our paper for the perovskites, you know. So we are running much longer simulations than the guys in this paper. So there is no exact answer to this, Helmut. And usually this is the question the referees ask. They say, oh, you haven't allowed the system to thermalize enough, and you have to run longer simulations. But in the range of picoseconds is something that is reasonable. Depends on the material as well and things like that.
Just to follow up on this, can you maybe a criterion could be if you do multiple simulations of the same thing and one long-term simulation, and when the average of all these multiple systems matches the long term of a single system, then you have the ergodic theorem reached, and then maybe could this be a criterion to apply?
Well, yes, it makes sense, Helmut. It makes sense, definitely. And but every time you start the material, the simulation here, for instance, you have to set a certain initial crystal structure, and then you let it move, okay? But we want the system to forget that initial structure. So if you run several small time simulations, is not good. Usually, the long simulation is much better than the other ones. And here, for instance, and then there are several different recipes. For instance, We do the same type of simulations with two different ways. This is we just set the system in a certain temperature and let it run. And here we do some ramp. So we start here from these structures, and then we run 30 picoseconds, and then we take this structure to run smaller temperatures. You see that the smaller temperatures, that they come from these high temperatures. So this is like a temperature. So there are a lot of recipes. There are a lot of recipes, and I cannot tell you whether one is, as far as I know, there is no consensus on whether different groups use different methodologies.
I was wondering why they use such a high temperatures for the beginning, but this is maybe just to save time. You go to a range where the diffusivity is so high that in a very short time you get the equilibrium structure, right?
Yeah, that's it.
And then you quench.
Then you quench. Exactly.
Then you quench.
And I thought that was really interesting as well. You know that they do, and it's tricky because you know, they say that they throw the atoms randomly through the system, but it cannot be exactly random because sometimes the atoms are too close to each other, then it's not going to work. It's going to explode, and it can cause some problems, you know. And so there must be some tricks they are not telling us, to distribute this kind of.
Of course, after some time, the structure will no longer be random. I mean, we know that in glasses, you know, you have attractive forces, ionic bonding, covalent bonding, so the silicon, the oxygens will like to cluster around silicon to form tetrahedral unities. So it doesn't matter too much, I think, if it's really completely random or not. You know, at 6,000 Kelvin, you know, the system will find the equilibrium configuration of the liquid.
But the problem is, how do you know that the two oxygens don't get bound to each other? I mean, they can, right, as well. But it seems that doesn't happen. They like to go one oxygen among two silicons, and that's
they will find their places.
Exactly.
They'll find their favorite equilibrium places. Anyway, there was a great discussion, and I invite you to have a nice coffee break and continue. Well, give him some break, you know, some 5 minutes to catch up, and then please continue to discuss this very interesting topic. And please be back before 4, say 5 to 4. You have 15 minutes. No, it's here. It's here. Coffee break is here. Thank you so much.
Thank you,
Gustavo.
Espera aqui. Tá bom? Ah, que bom.